So the following natural question would be, can we also apply these gradient descent approaches or function approximators to off-policy methods like the Q-learning method, one-step Q-learning or one-step TD Q-learning that we've seen before? And the answer is yes, we can also apply it there, right? But or we can also do learning approximation with bootstrapping. How can we do that? So that will still requires a small change from the tabular case. In the tabular case, if you remember, we updated our estimation of the state value for each state based on the temporal difference error, right, between the label, immediate reward plus a discounted value of the next state, minus our current estimation of the current state. So we simply, instead of updating, doing a tabular update, we can update our function approximator, our tunable parameters theta, in a very similar way to what we saw with the Monte Carlo approach, right? But instead of having a G, a capital G, as the ground truth, as the label that we're trying to fit, now we have the TD approximation as our ground truth, or as the label that we're trying to fit, right? And so that would be the immediate reward plus the discounted state value of the next state. So this is instead of the capital G that we've seen for the Monte Carlo case. And this is very similar to what we did also in the when we perform bootstrapping in the tabular setting, right? And of course now still, so you can think of that also as the derivative of the squared error loss, right? It translates to that. And again, we have to multiply that by the gradient of our approximator. This is known as semi-gradient methods, okay? This is applying gradient methods for TD on top of TD learning frameworks. These are not guaranteed to converge to a local optimum because of the approximation in our next state, right? Because this value is biased. It's biased by our approximation assumptions and some approximation errors that we might have. So that's a bias estimate of the true state value for the next state. And so usually semi-gradient or bootstrapping methods with gradients, with gradient descent or with approximation, they do not converge as robustly as full gradient methods. These are or do not converge as robustly as the Monte Carlo methods. However, in many practical uses, we still rely heavily on training a function approximator along with TD learning methods, because they do converge reliably in important cases, such as for linear approximation. Actually, if we use linear approximation, we can have some nice convergence guarantees. We'll see this later on. Actually, we'll see a specific method that relies on that ability. These methods, I'm talking about semi-gradient methods, they offer important advantages that make them often clearly preferred, and we'll discuss many of these advantages later on, and why they are such an advantage. Of course, we'll dive deeper into that. They typically enable significantly faster learning, as we have seen in chapter 6 and 7, right? The added bias is worthwhile due to the reduced variance, and that allows us to learn much quicker. They enable learning to be continual and online without waiting for the end of the episode, or without even requiring to learn in episodes like the Monte Carlo approach do. And so this enables them to be used on continuing problem and provides computational advantages. And as I said, we'll see this throughout the course moving forward. So let's look at the pseudocode for semi-gradient TD0. TD0, I'll just remind you, is the temporal difference variance that does one step look ahead. Why is that? I'll show you later on. This is as opposed to TD1. TD1 usually refers to the full Monte Carlo approach. And anything in the middle refers to different algorithms that are between them, but not the n-step bootstrapping, something slightly different that we'll cover later on. So the semi-gradient TD0 is very similar to the TD0 algorithm that we've seen previously, with one main difference. So what's the main difference here over the tabular case?
Function approximator?
That's true, but in the pseudocode, right? Where will that be?
In the weight update?
In how we update, right? How we update the approximate. Now we update an approximator, represented with the tunable parameters, in this case W, instead of updating entrances in a table that we did previously. Okay, so how do we update the tunable parameters? As we've discussed before, with by multiplying using the chain rule of the squared error loss derivative multiplied by the gradient of our approximate. Okay, let's see an example. Okay, so it's a very similar example to what we've seen before, but now we're going to do TD learning or TD semi-gradient learning instead of a Monte Carlo approach. So Vaibhav, can you walk us through this example?
So just like before, we have this Pac-Man domain with a state defined by a few features like distance to goods, distance to food. So we have two states here. From state S with features 2, 3, 1, we move to state S prime with state 2, 1, 1, 2, 1, and we get a reward of plus 10 upon doing so.
Right, so we have a full transition.
Yes.
State, action.
We don't have the action,
we don't have
but
the action. We don't need it because we're not doing Q.
From the picture, it looks like it went up.
No, it doesn't matter because in this example we're doing state values which are not action dependent. Right, for Q values we would need an action, but here it's actually, we don't need it. Okay, that's fine.
Yes. So we have a state, reward, and a next state. And just like before, we're using a linear function approximator, which we initialize to 0, to have weights of 0. And previously, we performed this update, like Dr. Sharon said. This was done in the Monte Carlo state case. This was G, but in our case, we are using our TD, seeing the observed reward and using our learned approximator to approximate the future discounted rewards. And this is essentially just the L2 gradient. And if you notice, in this case, we approximate the multiply the tunable parameters with the current state S and also the tunable parameters with the next state S prime to get its value. It's not back propagated as it was in Monte Carlo. During the computation, we learn a set of new weights, tunable parameters 2, 3, and 1. So now we want to, just like before, we want to see if the parameters that worked well in state S might benefit us in a different state U, which has similar features but a bit different. So we multiply the learned parameters with the state features, and we get a value of 17, which is I don't know if it's
it's fine.
because we don't know the value in this case, but it's probably more than 10 given our reward, so it's close.
Yeah. Okay.
Yeah.
Okay. Thank you. Let's move on.